Yeah. So the downside with doing this whiteboard is that the whiteboard was lost, but let me just share it to the link. Um, okay. Well, okay. Let me just display it for now. We'll see what we were doing earlier. So this is the previous proof I was looking at, right? This is the line we just discussed. That A is congruent to B modulo M if and only if M divides the difference. And I use this fact about uniqueness in the division algorithm. Okay, so now I'm going to use this to derive some interesting properties of modular arithmetic. So let me do that. So key properties of this notion of congruence modulo M. So one is if A is congruent to B modulo M, then the remainders are congruent. A mod M is congruent to B mod M modulo M. So what that means is if you reduce things modulo M, if you replace them by the remainders, the congruence still holds. That's not surprising because the definition of congruence was that they have the same remainder. So actually if A is congruent to B modulo M, then A mod M is equal to B mod M. And then certainly it's congruent to A mod M is congruent to B mod M. So that's not very surprising. Here's a more interesting one. If A is congruent to B mod M, or let me write it linearly like this, and C is congruent to D mod M, so these were just regular equations. You could add them and multiply them, right? But what this is saying is you can do that even modulo M. Then A plus C is congruent to B plus D modulo M. And AC is congruent to BD modulo M. Okay, so maybe before proving this, I'll give you an example. For example, let's look at 36 squared. So this is congruent to 36 times 36 modulo M, modulo 7, let's say. But now, well, 36 is, what is 36 congruent to modulo 7? Well, many things, but what's the simplest thing?
1.
1. Because 36 is equal to 7 times 5 plus 1, right? The remainder is 1. So by this property number 2, what this is saying is this is congruent to 36 times 1 modulo 7, right? Because 36 is congruent to itself and 36 is congruent to 1. And then I can do this again and get this congruent to 1 times 1 mod 7, which is just 1. Right? So here I use by property 2. And this is kind of amazing because notice that I never computed 36 squared in this, right? I computed the remainder modulo 7 without actually computing 36 squared. So the upshot is you can reduce numbers modulo m before doing the arithmetic, and it doesn't change the answer. Right? Because this number, this is some, I forget what this is. I think this is 1296 or something, right? That's a lot harder, right? I have to do some arithmetic with big numbers. But the beauty is, even if I just know the remainders of the numbers I'm multiplying, that's enough to figure out the remainder of the product. That's what this key properties are saying. That the remainder of the product can be determined just by knowing the remainders of the individual terms, and similarly for the sum. So this answers the question somebody asked earlier. Could you replace things by their remainder modulo 7 during the computation? The answer is you can. So any questions about this? So this is one, and then the other upshot is, can do algebra, by which I mean addition, multiplication, substitution of equations as usual, right? Congruence is not the same thing as equality, but what these properties are saying is that for the purposes of doing addition, multiplication, and substitution, they are. So before I prove there's any questions about what this is saying.
Sorry, that's substitution of what?
Like substitute one equation, like here, I mean.
Oh, I just couldn't read what it says.
Oh, sorry, yeah. So for example, here I use that 36 is congruent to 1. And then I substituted 1 for 36, right?
But just in the last line, does it just say substitution of equations?
Oh yeah, sorry, of equations.
Thank you.
Handwriting is bad.
Could you explain real quick again what's like the definition of congruence?
Sure.
Thanks.
So the definition of congruence is here in the previous slide. So two numbers are congruent modulo m if they have the same remainder modulo m. A mod m equals b mod m. And by this proposition, that's the same thing as saying m divides a minus b.
So like the mod m on the right side of the doesn't mean it just do operation to b's for both a and b.
Yeah. Okay, good question. So the notation, yeah, so good. So let me make a remark. A is congruent to B mod M. This doesn't mean you compute the remainder of B. That's why you put the parentheses around the mod M. This is not the same. This is not the same thing as saying, A is congruent to B mod M, which actually this doesn't even make sense, right? So in fact, in general, this doesn't make sense without a parentheses mod M. Why is that? Well, because the M is part of the definition, right? I mean, whether or not two numbers are congruent mod M depends on what M is. For example, 3 is congruent to, I don't know, 1 mod 2, but 3 is congruent to 0 mod 3, right? So if you change the M, then numbers which were congruent may not be congruent anymore, right? So 3 is not congruent to 1 mod 3. So this M is very important. You must always keep track of this M. Okay, is that clear?
Yes, thank you.
Right. So this is a definition that applies to a pair of numbers, right? A and B. It doesn't just, it's not an operation that just applies to one number. Okay, so let me prove some of these properties on the key properties. So one, I already told you the proof. So let me prove item 2. So in item 2, there were 2 things, addition and multiplication, right? So addition, let me do addition. So assume A is congruent to B mod M and C is congruent to D mod M. So I'm going to use this divisibility characterization, right? So by proposition 1, this means M divides A minus B and M divides C minus D. But now by the proposition I proved in the beginning of the lecture, let's call that proposition 0, M has to divide the sum. Which, rearranging the parentheses, is just M divides A plus C minus B plus D. So what does that tell me about A plus C and B plus D?
They're congruent.
They're congruent by proposition 0. Modulo M. So this is not complicated. It goes back to the fact that if A divides B and A divides C, then A divides B plus C, right? The proposition we proved at the beginning. Let's do multiplication. That's a little bit more interesting. It's actually, multiplication is the first one where if you just try to do it sort of in a bare way with the definition, it doesn't really work out. So let's see. So again, assume A is congruent to B mod M and C is congruent to D mod M.
Wait, sorry, can you go back to the previous one for like 2
Sure.
seconds?
Sure, sure.
Thanks. Okay, thank you.
Yep. So now our goal is to show that AC is congruent to BD mod M. We're going to do this slowly. And it's actually kind of tricky. When I was preparing the lecture, I didn't get it right away. So let's see, what did I do? Yeah, I did this. So by proposition 1, M divides A minus B. And consequently, well, or let me just unwrap it since we haven't done this before. So A minus B equals Km for some integer K, right? But now I'm going to do a little trick, which is just another basic property of divisibility. Observe that, or let's just say this implies that if you multiply both sides by C, it's still true, right? C times A minus B equals CKM. So actually, M divides CA minus CB. And again, by proposition 1, that means CA is congruent to CB mod M. Okay, so here I'm using sort of an easy fact about divisibility, that if A divides B, then A divides BC for every integer C. That's the fact that I used. I can throw in the C for free. Any questions about that little argument? So I went from A congruent to B mod M to AC congruent to CA congruent to CB mod M. Okay, so now by the same argument, I can take the other congruence, which is that C is congruent to D, and multiply both sides by B, right? CB is congruent to DB mod M. So by the same argument is again a useful piece of writing that's used a lot in mathematical writing. It's saying that I don't want to just copy that text again. I'm just going to do the same thing again, but with these different numbers that behave in exactly the same way. So now I have these two key equations here. Any ideas about what I could do with them?
We can, okay, so effectively we can do substitution.
Yeah.
Yeah,
The reason you can do substitution is that, I mean, I'll just make it painfully clear for you. So, let me just unravel the definition, right? Then AC mod M, so now this is the remainder, equals BC mod M equals BD mod M. I mean, here I switched the order of the numbers. That doesn't matter. Multiplication is still commutative. I'm just going back to just good old equality of numbers here. Right now, the first fact I got from the first equation, and the second fact I got. You're not what? Sorry, was there a problem?
I think someone was just unmuted.
Wait, it said I stopped sharing.
Yeah, but it's back.
Okay, I'm really sorry that this is okay. Can you see the screen?
Yep.
Okay, great. So yeah, so in the first equation here, I'm using the first congruence. In the second equation, I'm using the second congruence. But then this is what I wanted, right? So AC is congruent to BD modulo M. That's desired. So any questions about this proof? The key fact I used is this little fact about division, that if A divides B, then A divides BC. That's always true. So I can multiply both sides of congruences by the same number. But I needed to justify that. Okay, so using those basic properties. So the upshot really is that this thing that you can simplify, you can reduce modulo M before doing the arithmetic, and you get the same answer. That's not obvious, and that's a very powerful thing, as we'll see in a moment. Any questions before I go to the next section?
So when you're like doing the proof of prop 1, U times C, like thus implies that C. So can I do D? Will I get the same result?
Oh, you mean you can use D instead of C in this proof?
Yeah, so yeah.
Yeah, you could. It would work in it. You would start with probably with BD, but yeah, it would work.
Like for the second part that you use red pen to circle by the same argument, is that mean that you did the same process just using C and D?
Right. So
Yes,
you do
sir.
the same argument applied to B.
Oh, so it's implied B times C minus D.
Yeah, yeah. You apply B to
Oh,
the other
okay.
congruence. So yeah, you're right. I should make the writing even clearer. Applied to the other congruence. Applied to B with the other congruence. That would be a better way to write it. Yeah, good point. Okay, so let's now move on to the last topic. Which is representations of numbers. Okay, so the representation of numbers we use on a daily basis is called decimal. So let me just spell out what that is. So so let's see. So in decimal, the number, let's say dk minus 1 all the way up to d0, with all of these digits being in 0 through 9, refers to d0 plus d1 times 10 plus d2 times 100 all the way up to dk times 10 to the k. I guess we all know this, right? So that's the correspondence between the digits of a number and the number itself, right? The different places correspond to different powers of 10. And so I want to prove one sort of cool fact about divisibility that becomes clear when you use modular arithmetic that you may have heard of before. So here's a proposition, proposition 2. And the proposition is let n be a positive integer. And suppose its digits are dk minus 1, all the way up to d0. Then the number is divisible by 9, if and only if the sum of these digits is divisible by 9. So this is a fact which I think I learned in grade school, but I didn't learn the proof, actually. And so, you know, for example, what they're saying is that 9 divides, I don't know, 2, 6, 9, 8, if and only if 9 divides 2 plus 6 plus 9 plus 8, which is 9 divides, what is that, 8 plus 8 plus 25, which it doesn't, right? So you can easily check that 9 doesn't divide this huge number just by checking the small divisibility. It's kind of striking, actually. So I'm now going to prove this using modular arithmetic. Okay. So let's see the proof. So I'm given a number with these digits, right? So suppose n has these digits. N equals d0 plus d1 times 10 plus d2 times 10 squared dot 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 dk times 10 to the k. And I'm going to use the summation notation. I equals 0 to k di 10 to the I. And this is a notation we're going to be using a lot in this course. So this is the first term of the sum, the first index, and this is the last index. So it's saying I'm adding up di times 10 to the I, where I goes from 0 to k. Okay. So now I'm interested in whether this is divisible by 9, right? So it makes sense to figure out what the remainder is, modulo 9. Now the key thing that the reason this works out is that there's something very special about 10. So notice that 10 is congruent to 1 modulo 9. And what about 100?
Same.
Yeah, 10 squared is congruent to 1 times 1 mod 9. And in general, 10 to the any power is congruent to 1 to that power modulo 9. So it's just congruent to 1. And here I'm using the properties, right? I'm using that I can reduce the number before doing the arithmetic. By the properties of this congruence, I have all these things. Okay, therefore, n, which is congruent to this number, in fact, it's equal to this number. I can just substitute in what the 10 to the i's are congruent to, and those are just 1. This is congruent to. Any questions about that step? But then that's what I wanted to prove, right? I proved something even stronger. I proved that they have the same remainder. So thus, 9 divides n, if and only if 9 divides the sum of the digits of n. So that's the proof of this fact, this divisibility test for 9. Okay, so now I want to briefly talk about how do you represent integers in other number systems. So decimal means you write numbers as sums of powers of 10. But there are other number systems. So in base B, we write numbers as sums of powers of B. Okay, so in particular in binary, so the binary is B equals 2. So for example, here's a number 101101. I'm going to write it subscript 2 to indicate that the interpretation is this is a number in base 2. Is the number 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 to the 2 plus 1 times 2 to the 3 plus 0 times 2 to the 4 plus 1 times 2 to the 5. Okay. So, well, in this case, what number is this? Well, let's just find out. So that's just 1. So the first term is 1, second term is 0, third term is 4 plus 4. Fourth term is 8 plus 8 plus 0 plus 32, which is the number 45. Okay, and the digits in base B are the coefficients of the powers in B, right? So the, I don't know, if yeah, the digits in base B are the coefficients of these powers. So it's not that different from decimal, it's just binary. This is the least significant digit. And this is the most significant. Just like we do with digits. We have 10 fingers, we don't have 2 fingers. If we had 2 fingers, we would be probably doing this. So now I'm going to show you how do you convert numbers from decimal to binary with an example. And the algorithm is going to involve this division algorithm that we learned. Okay, so how to convert? The binary. Let's look at an example. Let's look at the number 45. So the idea is repeatedly divide by 2. So let's divide 45 by 2 in the sense of the division algorithm. 45 divided by 2, so this is 2 times 22 plus a remainder of 1. And now let's look at the quotient and repeat. Let's divide that by 2. So that's 2 times 11 plus 0. And then let's do it again. 11 is 2 times 5 plus 1. So repeatedly divide the quotient by 2 is what I'm saying. And now I take this 5 and I again divide it by 2. That's 2 times 4 plus 2 times 2, sorry. Plus 1. And then the final, this one is 2. So 2 is 2 times 1 plus 0. Or, sorry. Yeah, 2 is 2 times 1 plus 0. And 1 is 2 times 0 plus 1. So keep doing this until you get stuck, right? Until you get to a point where you get a number less than 2. Okay, so here's something interesting. Let's read these remainders from top to bottom. That's the same as the binary expansion I started, 1 0 1 1 0 1. Okay, so the punchline is that the remainders are the digits in the binary expansion. In the binary representation, let's call it. Of 45. Right? 1 0 1 1 0 1. Now that's not an accident. Let me give you the reason. It's not a proof, but in this example, let me give you the reason. Well, what have we done? We've said, well, 45 is equal to 2 times 22 plus 1, which is equal to 2 times 11 plus 0 plus 1, which is equal to 2 times 2 times 5 plus 1 plus 0 plus 1, which is equal to 2 times 2 times 2 times 2 times 2 plus 1 plus 1 plus 0 plus 1, and so on, right? So in the end, we've expanded 45 in this way. And if we open the parentheses, we're going to get a bunch of powers of 2. And the key point is that the ith remainder is going to get multiplied by 2 to the I when we do this, right? So observe that the ith remainder is multiplied by 2 to the I. So really, when we're doing this repeated division and recording the remainders, we're actually recovering the coefficients in front of the powers of 2 to the I. So I'm not going to formally prove this. We may formally prove it later. So skip formal proof for now.
So like if it's base 3, 4, we can use the same.
Yeah, so it's a good point. So in general, to find base B representation. Step 1 is repeatedly divide by B until you reach a number strictly less than B. And then step 2 is just output the remainders from top to bottom. Okay, so I didn't get to answering our challenge question of what day is it in 5 to the 45 days, but I'll do this next time, and it will involve the binary representation. Anyway, that's it for today. So thanks.
Thank you.
Thank you. Bye.
Thank you.
Thank you.